Recent advancements in computer science robotics have been synthesized from 23 papers published on April 29, 2025. This multidisciplinary field integrates artificial intelligence, engineering principles, and control systems to create sophisticated robotic solutions. Key application areas include autonomous vehicles, medical robotics, and industrial automation systems. The research primarily focuses on enhancing three critical aspects: system robustness in unpredictable environments, efficient coordination between multiple robots, and advanced learning capabilities for real-world deployment. These studies collectively push the boundaries of what robotic systems can achieve in complex operational scenarios. Computer science robotics, often referred to as CS/RO, serves as a bridge between perception, decision-making, and physical actuation. This field combines expertise from computer science, mechanical and electrical engineering, along with artificial intelligence to solve challenging real-world problems. Current research emphasizes autonomous navigation capabilities, precise manipulation techniques, and adaptive control systems. Notable recent advances include improvements in multi-agent system coordination, development of more responsive adaptive control algorithms, and innovations in human-robot interaction paradigms that enable safer and more intuitive collaboration between humans and machines. A predominant research theme addresses uncertainty and robust control in robotic systems. Zhang and colleagues developed a novel approach using Koopman operator-based nonlinear model predictive control for navigation in stochastic environments. Their key innovation involves transforming nonlinear dynamics into a linear subspace representation, enabling more reliable operation when facing sensor noise or environmental unpredictability. This method demonstrated significant practical impact, showing a 30% reduction in collision rates when tested in cluttered environments compared to traditional control approaches. Such advancements are crucial for deploying robots in real-world settings where conditions cannot be perfectly predicted or controlled. Multi-robot coordination emerges as another critical research focus, particularly for heterogeneous robotic teams. Al-Ghamdi's team introduced an opinion-driven framework that effectively prevents deadlocks when multiple unmanned aerial and ground vehicles operate in confined spaces. Meanwhile, Mondal and collaborators achieved a 40% improvement in mission completion times through their deep reinforcement learning approach to energy-constrained routing. While these methods show promise, they highlight an ongoing challenge: balancing computational complexity with the need for real-time decision-making in dynamic environments. These coordination algorithms are particularly valuable for applications like search and rescue operations and large-scale logistics. Learning-based manipulation represents a third major research direction, employing techniques ranging from reinforcement learning to diffusion models. Zhang's XPGRL framework for mechanical search tasks demonstrated remarkable efficiency gains, achieving 4.5 times improvement over previous methods. Liu's work on topological dynamics modeling enabled robots to handle complex tasks like folding intricate clothing items. A significant breakthrough in this area involves combining reinforcement learning with explainable action primitives, allowing robots to not only perform tasks effectively but also provide understandable rationales for their decisions. These advances are transforming robotic capabilities in manufacturing, healthcare, and domestic applications. Several key findings stand out across the reviewed papers. The Koopman operator-based nonlinear model predictive control approach has proven particularly effective for robust navigation under sensor noise and environmental uncertainty. In multi-robot systems, deep reinforcement learning methods like those developed by Mondal's team have reduced mission times by 40% compared to traditional heuristic approaches. Meanwhile, Mitchell's work on compliant control systems achieved sub-centimeter precision in manipulation tasks, demonstrating the potential for highly accurate robotic applications in precision manufacturing and medical procedures. These collective advances are expanding the operational envelope for robotic systems across multiple domains. The reviewed papers share several common methodological approaches. Nonlinear model predictive control, or NMPC, emerges as a preferred technique for optimizing robotic actions while respecting operational constraints, though it faces challenges with computational intensity. Deep reinforcement learning offers scalable solutions for complex decision-making problems but requires substantial training data and may lack interpretability. Invariant filtering techniques, particularly those based on Lie algebra, provide robust state estimation capabilities but demand careful sensor model calibration. Each methodology presents unique trade-offs between performance, computational requirements, and implementation complexity that researchers must carefully consider for specific applications. One seminal paper by Zhang and colleagues in 2025 presents a Koopman operator-based nonlinear model predictive control framework for mobile robot navigation. The research addresses critical challenges posed by navigation uncertainty, including wheel slipping and sensor noise. Their solution involves learning bilinear dynamics representations through randomized control inputs during training. Hardware validation demonstrated the method's effectiveness in real-time operation, showing superior robustness compared to conventional approaches. This work represents an important bridge between data-driven learning techniques and model-based control paradigms, offering improved reliability without compromising real-time performance requirements essential for practical robotic applications. Mondal's 2025 paper introduces a transformer-based deep reinforcement learning framework for coordinating unmanned aerial and ground vehicles with energy constraints. The innovative system optimizes both task allocation and recharge scheduling through sortie-wise agent switching. Experimental results showed a 40% reduction in mission completion times compared to heuristic baseline methods. Notably, the framework maintains its effectiveness in dynamic environments, demonstrating scalability for large multi-agent teams. These capabilities make the approach particularly valuable for extended duration missions in logistics and emergency response scenarios where energy efficiency and coordination are paramount concerns. Mitchell's 2025 research on dual-arm compliant control represents another significant contribution. The team developed a hybrid impedance controller operating in both joint space and task space, incorporating a model-free observer to compensate for friction effects. Validation on a Canova Gen 3 robotic platform demonstrated sub-centimeter precision in delicate tasks like pin insertion. Perhaps equally important, the researchers made their implementation openly available on GitHub, significantly lowering barriers to adoption for both academic and industrial applications. This work advances the state of compliant manipulation, enabling safer human-robot collaboration and more precise industrial automation processes. Looking ahead, several key challenges and opportunities emerge for computer science robotics. Real-time computation remains a critical hurdle, particularly for deploying computationally intensive methods like nonlinear model predictive control and deep reinforcement learning on edge devices. The sim-to-real transfer problem continues to limit practical application, as policies trained in simulation often fail when faced with unmodeled real-world dynamics. Ethical considerations surrounding autonomous decision-making systems are gaining prominence, necessitating the development of robust frameworks to ensure responsible deployment. Addressing these challenges will require continued innovation in algorithm efficiency, simulation fidelity, and interdisciplinary collaboration between technologists and ethicists. Three key takeaways emerge from this synthesis of April 2025 robotics research. First, robust control methods like Koopman operator-based nonlinear model predictive control are enabling more reliable deployment of robots in unpredictable real-world environments. Second, multi-agent deep reinforcement learning approaches are unlocking new possibilities for scalable coordination in logistics and emergency response scenarios. Third, advances in compliant manipulation techniques are bridging the gap between industrial automation and delicate medical applications. Together, these developments are expanding the boundaries of what robotic systems can achieve across multiple domains of human activity. This presentation was created through a combination of artificial intelligence tools and human expertise. Advanced language models assisted with content structuring and summarization of the technical papers. Text-to-speech synthesis provided initial audio review capabilities, while text-based descriptions facilitated visual content generation. Throughout the process, human experts maintained oversight to ensure technical accuracy and narrative flow. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the ArXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.